Okay, we're just going to continue from last section of notes, and we were talking about the norm. Okay, and again, this is the longest subinterval of any of these subintervals that we divide our interval into. These are what we call subintervals. And remember, the longest subinterval, and again, we said these can vary. And when we were doing our RAM and LRAM and midpoint RAM, just for the sake of calculation to make it a little bit easier, we're using the same length of subinterval, but they don't have to be. But the idea, the main idea is the longest subinterval is called the norm of the partition, okay, of this particular partition that we use to divide this interval up into these subintervals. Now, as the norm gets smaller and smaller, in other words, as the largest subinterval gets smaller and smaller and smaller, then what's going to happen is our subintervals are all going to approach 0. In other words, as our norm approaches 0, and in other words, as the length of the smallest of these gets smaller, I'm sorry, the largest of these, because the norm is the largest subinterval, as this gets smaller and smaller and smaller, if that's the largest, that means all the other ones get smaller and smaller. So they all approach 0 as the norm approaches 0. That's the idea. Okay, so let's take a look at some more of these notes. And again, you can put these in your binder as notes. That way you won't have to, write these down. Okay, so the definition. The definite integral as a limit of Riemann sums. Let f be a function defined on a closed interval, a, b, for any partition P. Remember, that's how we divide up the subintervals of a, b, and let c sub k be chosen arbitrarily in the subinterval. We talked about that. And so again, c sub k is this number here that we're going to pick in the subinterval, and we're going to use that to determine the height of our rectangles. Okay? If there exists a number I such that the limit as the norm approaches 0 of the sum of all these rectangles, if I add up all the areas of these rectangles, all right, if I have a particular area that I can come up with, as the norm approaches 0. Now remember, as the norm approaches 0, as my base of all these rectangles gets smaller and smaller and smaller, I have more and more rectangles, okay? And eventually I have as this approaches 0, the number of rectangles I have will be approaching infinity. All right? I hope that makes sense. In other words, as I make these smaller and smaller, I'm going to get more and more rectangles. As it approaches 0, the number of rectangles approaches infinity, and which is going to give me pretty much the exact area under that curve. Okay? So what Riemann says, if there exists a number I such that the limit as the norm, the largest subinterval approaches 0, or in other words, you can say the number of rectangles approaches infinity, of the sum of all these areas, if that equals some number I, no matter how P and how the C sub k's are chosen, then the function f is integrable on AB. And I, that value of all these areas, that's the sum of all these areas, is the definite integral of f over AB. So that's going to be the definite integral. That's what the I stands for, and that's the sum of all those areas, which is just what we were approximating. We were approximating those values using LRAM, RRAM, or MRAM. Okay? And the very important theorem here, the existence of the definite integral, and these are all proven in advanced calculus classes because these are pretty tricky to prove these. The existence of definite integrals, all continuous functions are integrable. In other words, if a function is continuous, we can find the area, the exact area. This is the exact area under the curve. That is, if a function f is continuous on an interval ab, then its definite integral over ab exists. Definite integral of a continuous function on ab, let f be continuous on ab, and let ab be partitioned into n subintervals of equal length. Delta x is b minus a over n. Now, what basically is this saying, this is how we can subdivide these. Delta x, if these were equal length, and again, this is for notation, and this is also for, we can do this, and we do this to make our calculations a little bit easier so we can't factor out that base, and we were doing that in our LRAM, RRAM, and MRAM. In other words, if I have this length, b minus a, in other words, the length of the subinterval from a to b is b minus a, and if I have n of these subintervals. If I divide that by n, I would get the length of each one. So that's all we're doing. So we take the length of the subinterval, which is b minus a, and divide it by the number of subintervals, and we get the length of each subinterval. Okay, that's what this represents. If we call this delta x, then the definite integral of f over ab is given by this, the summation, that equals the limit as n approaches infinity of the summation of all these areas, and the bases are all going to be the same. Now remember, when we did our LRAM, MRAM, or RRAM, we could factor out that base, and it made it a little bit easier when we did our calculations. So that's what we're doing here. We're going to use the same base because we're going to use equal subintervals, where each c sub k is chosen arbitrarily in the subinterval. Okay? All right. And then we're going to talk about this as n approaches infinity. So as the number of subintervals approaches infinity, as the number of subintervals approaches infinity, that's the same thing as saying our partition approaches 0. Okay? Okay. And you can sometimes think of this as now we've talked about this before, how the limit, remember the limit as delta x approaches infinity of the change in y over change in x, or the or our, should I say, as our slope is equal to the derivative. Well, we have the same idea over here. The limit of this as n approaches infinity of the summation of these areas equals what we call an integral. And we'll talk about that. We have to go back and take a look at our book, so let's talk about that in a moment, okay? So we'll do that on the next notes. But this is going to be what we call an integral. But this is basically just a different notation for this. And it's like this is a summation, and this is a Greek summation. Sigma for S in Greek for sum, and this is an S in a Roman, kind of abbreviated or kind of elongated S, all right? And the delta x becomes a dx. This is our function at some particular x, and this is the interval in which we're finding the sum of the areas, okay? We'll talk about that. That's over in your book on page 277, and we'll get that in just a moment here. So it'll be on the next notes.